We're recording. We are recording. Yay. All right. Oh, nice. Okay, so what we got here. Okay, what is the Pythagorean theorem? You know this pretty well, but it's the first day back. What is the Pythagorean theorem, and what are some interesting facts about the life of Pythagoras, if you know any?
He was born in 1400.
A squared plus b squared equals c squared. Yeah. What else could we draw something to explain this thing as well? Is there something we can draw? What do they relate to?
Right angle triangle.
Right angle triangles. Yep. The board is getting worse calibrated as we speak. Right angle triangles. Let's see. Have I labelled it correctly?
No.
What did I do wrong?
The C goes on the longest side.
Yeah, good. That's right. The hypotenuse. Oh, great. So the hypotenuse is the longest side. This thing's gone mad. The hypotenuse is the longest side. I might have to write on here. Okay, C. Does it matter which one is A and B?
No.
No. What do we call this funny side C?
Hypotenuse.
Hypotenuse. Yeah, that's an important word. Let's practice that one. Hypotenuse. Do you know what we tend to call the other two sides?
Non-hypotenuse.
Like parts of the body?
Yeah.
Oh, when we do SOHCAHTOA, yeah, we do trig ratios, we tend to call them legs.
Yes.
Yeah, we call them legs. When with regards to Pythagoras' theorem, we call these two sides the legs.
Can you stop? Can you stop?
Confusing. Okay, so we've got the two legs. The legs form a right angle, and the hypotenuse, like Sarah said, the hypotenuse is the longest side. So the board is again, gosh, I'm just going to write it slowly. The hypotenuse is the longest side.
It doesn't look that dodgy. Dodgy? Fine.
Okay, I'm just going to pause.
Look at the H.
It does.
The other H.
I know, it does look pretty bad. Okay, I'll just quickly pause this because yeah, it could be. Like, how long ago was it, roughly?
Yeah, how do you even know that?
Exactly.
It's how you find it.
It was in BC. Anyone have a rough idea?
495.
Right. I was going to say around 500, but that's probably not correct.
You have a tag. I said 495.
Oh, did he?
I bet he wasn't really a cult leader.
Yes, you can. Yeah. So cult leader, Pythagorean order, around 495 BC. What did he have an irrational fear of?
Beans. Wait, Miss Melanie, why do I Pythagorean order? That was just
No, that was the name of his cults.
What's his name?
Pythagoras.
Oh.
That was stupid. He had a fear, you didn't know that, it's okay. Had a fear of beans. And on stupid deaths, why did his fear of beans lead to his death?
Because he was running from some people and they caught him.
Yeah, he wouldn't run through? Yeah.
That's how he died?
Yeah.
Because he was lazy.
Were you not listening?
It was pretty to have a second and I was really confused.
Yeah, so he wouldn't, people were chasing him to kill him, according to this story anyway. And he wouldn't run through the bean field because he's orderer.
So the father died. Beans contain human souls. Okay, now the beans have human souls.
How did he even know that he had a fear of beans? How did they know that?
Because his people believed that beans were also had human souls.
How did they even know that?
Exactly.
They're awesome. That's cute.
How do we know?
People make these people up. Why did they have a
They need diaries and stuff.
Running from assassins there. You don't run into your own field.
Cool, just in case. All right, SOHCAHTOA. We're on to SOHCAHTOA now. Let's label the hypotenuse, opposite, adjacent, and right of the right angle triangle below, and then use SOHCAHTOA to fill in the missing parts. Feel free to race ahead and try it yourself first if you prefer.
Do do
Or do
what?
you want to just do it as a group?
I wasn't really listening.
So by hypotenuse, okay, I'm gonna have to do it. I thought this room was a good room for a board. Yeah, so just first of all, we'll label. Remember, when we use adjacent and opposite, we tend to use capital letters. So is this one over here, is this adjacent or opposite the angle?
Opposite.
Good, yep, opposite, yep. And adjacent means kind of next to, kind of. So the one next to the angle. So Calvina is adjacent to Kiesia.
Calvina is opposite from me.
Yes, exactly. Yes, you can, sure thing. If you
That's the hypotenuse.
Okay, so using the SOHCAHTOA thing, you already probably know, sine theta equals?
Opposite over hypotenuse.
Well done, good. And similarly, if you wanted to solve for theta instead, for the angle, which is the Greek letter theta equals inverse sine.
Inverse line.
Yeah, same thing in here, yeah, O over H. Inverse sine, which you guys are probably pretty good at already. Same thing, you probably know these ones. Sorry, because the board's a bit dodged, that's why I'm doing it on here. O over A. And then the same things over here.
You press second.
Oh no.
Use my bubble.
He doesn't even work at home in circumcision.
It's probably like stuff you know already. So, you guys were talking about it. What do you press on your calculators, the TI-84? What do you press to make sine minus 1 happen?
Second sign.
Second sine, yep.
Go star for you.
Second sine. And it can vary a lot. Like if you're on the TI Inspires, the different calculators like the IBs are on, they just go to a Trig button. And then when they press Trig, all these other buttons open up and they have to select sine minus 1.
My calculator has special buttons for everybody in
lying
here.
around that you don't want anymore.
Do you need to buy a new one? Are you sure? Have you had a good look at home though?
I know it is. It's just broken.
Oh, it's broken. Maybe it just needs new batteries.
Like
4 AAAs. Yeah, I think they have 4 AAAs.
AAAs?
Yeah, 4 AAAs at the back. Oh, no. The old ones did. No, you charge it, yeah. Have you charged it? Maybe just your charger's broken.
like it only works when you charge. And when my exam comes, I'm in the middle of the room. We're gonna have a problem.
Okay. Maybe just double check it with someone else's charger just to be on the safe side. Maybe it's or I could stick it in the big charging dock and see if that works as well. Because quite often the charging wires are very flimsy and quite often the charging wire is broken.
No, like it works when the charger charges it, but if I take it off the charger, it will just shut off.
Okay. We could double check it with one more just in case there is something dodgy. Yeah, they're a bit dodgy, aren't they? It's annoying. Hope it comes back to life. Okay. So going on to special triangles and the unit circle. So this is something that might have just been brushed over a little bit because it wasn't a big feature of the CIE and it's been a few years. So there are 2 different types of special triangles which can be drawn in the unit circle. Work out the missing angles and side lengths and describe each triangle under the diagram. So what's that little angle there?
Right angle.
90, yeah, exactly. And so what's this little angle here got to be?
45.
Yeah, how did you get that?
Because the other one's 45.
Good, yeah, 45 degrees, yeah. Don't forget your little degree sign as well. Be nice and strict with the little units, because we don't know whether you mean 45 degrees or radians. So putting a little thing there. So what kind of it's right angle triangle. There's another way you can describe it. Equilateral, yeah. Therefore, what would be that little length here?
1.
Oh, yeah, because it's not equilateral. Sorry, what is it?
What?
Yeah. I don't know what I'm talking about. It's something else though. Isosceles, yep. So let's write that under there because we have to sort of describe the triangle. So it's an isosceles triangle.
Wait, isn't isosceles 2 lengths of the same?
Yes.
45 and 45, dog.
Yeah, you have to see it. So isosceles triangle, 2 lengths are the same and 2 base angles. So the base angles and the length are the same. But if it was equilateral, all 3 angles would be 60. So that's clearly not equilateral, like I said. We need to work out this missing side here. There's probably all sorts of different ways we can do it. What might be a simple, easy way we could work it out as a third? Pythagoras, yeah.
Is it as a third?
Yeah.
Root 3.
It's root 2.
I was just guessing.
Could be root 2. And if you weren't sure, how could you use Pythagoras to work it out?
Is it just 1 squared plus 1 squared equals
Oh, you did?
Is it one?
Is it just 1?
Yeah.
1 plus 1.
2. Yeah.
So imagine it was x.
2.
Yeah, so it would be the x would be the, because it's a hypotenuse, square root of, 1 squared plus 1 squared using Pythagoras' theorem, which is root 2. So let's put that in. So it equals, oh God.
I remember this. We had a whole table for the random ones. Random ones. They were like irregular.
I'll just do it here. Okay. Oh, God. Okay. So these boards are shocking. Okay, so x equals root 2. Root 2, which is what we worked out down here. Using Pythagoras. So it's a hypotenuse, root 2. And there's no units, so we just write root 2. You could write units if you want. So it's an isosceles triangle. And so its 3 sides are, so if you've got a 45 degree triangle, angle triangle, then the sides we generally say, oh, if that's 1, then it's 1 and root 2. That's a special triangle, 1, 1 and root 2. And we're going to use that to fill in some things later on. Oh, and I didn't put in 45, that's okay. This little baby here, so we've got 60 degrees here, we've got 90 there. What must this angle here be?
30.
30, good. How did you get 30 degrees?
I did 90 plus 60, which is 150. And then 180 subtract 150.
Totally, yep, that's good. Subtract from 180, nice. Okay, is it a equilateral triangle?
No.
No. Is it an isosceles triangle?
No.
Is it a scalene triangle?
C.
Yep, so maybe let's just write that. It's a scalene triangle. Just to practice the type of triangles. Scalene triangle. We need to work out this little missing side down here. Let's call that x. So, can we use Pythagoras? We could use Socotora as well, but imagine we didn't have a calculator, so Pythagoras would be a bit easier. How could we work out what x is in this case?
Square root. No, C squared minus 1 squared equals x.
Yeah. Yeah. X squared, yeah. So if you went straight to solving for x, you could go x squared equals 2 squared minus 1 squared by rearranging Pythagoras. If you go straight into it, we do this.
Great.
So therefore equals square root of 3, yep. That's the other side. So x in this case equals square root of 3.
I said root 3. I was looking at this one.
So on a special triangle, if you've got a
Does
45...
it C have to be the hypotenuse?
Oh,
Miss Maloney?
yeah?
Doesn't C have to be the hypotenuse?
Right. Seriously.
Yes, it does.
Yeah.
Oh, but I called it x. I'm not calling it c. I'm calling it x. Oh, you're talking about this one. So notice, yeah, c does have to be the hypotenuse.
Which triangle you want? Because you need to on the first one.
Yeah, so c, in this case, we were working at a hypotenuse, so we had to do 1 squared plus 1 squared.
Yeah.
And then to solve for c, we had to square root, because c squared equals that. Whereas here we had the hypotenuse already.
Yeah.
So that squared plus that squared equals that squared. So to rearrange, we do that squared minus that squared. Will give us that squared. So that's why we did the hypotenuse squared minus the other leg squared, and we square rooted it to get it by itself.
You can do that?
Yeah, you can go straight to rearranging it if you're comfortable with that. But if not, you can just put it into a squared plus b squared equals c squared, and then slowly kind of rearrange it that way. That's fine too. You work it out whichever way you're comfortable with. I'm just being late because the board's so dodge, so I'm trying to avoid writing as much as possible. That's the only reason why I'm writing it out so badly.
Oh, when you say, yeah, I understand.
Yeah, so there's the 3 lengths. And so this one was to work out that one, and this one was to work out that one. And an isosceles triangle kind of enabled us to work out that one. Okay, I'll just quickly save that. So now let's, for the next ones, use the above special triangles and Socotoa. Find the values of the following, leaving your answer as a fraction or a third. So sine of 30, will I look at this triangle? No, I should look at this one, shouldn't I?
Yeah.
And sine, remember, is opposite over hypotenuse. Yep, good, 1 over 2, exactly. So as a fraction, sine of 30, opposite over hypotenuse, so 1 over 2. You can write O over H first if you want, but again, I'm avoiding writing because my board is so bad now. 1 over 2. So, because I said leave your answer as a fraction or a third in this case, just because that's how we kind of tend to do it. Whereas if we did sine of 60, yeah, good. No, whoops. Sine of 60 instead, the opposite will be root 3 and the hypotenuse will be 2. So if it's sine of 60, opposite over hypotenuse is, as Isabella said, root 3 over 2. So we leave that as a fraction, don't turn it into a decimal and round it. These are called exact values because we're not turning them into decimals and rounding them.
Wait, I'm confused.
Yeah, back to this one. That was sine of 60. So sine of 60, we've got to look at this triangle.
Never mind.
No, it's okay.
I have my O and H is messed up.
Oh, okay, O and H, yeah. And then let's go on to cos of 30. Cos of 30, adjacent over hypotenuse. What would that be? Yeah, root 3 over 2. Adjacent to 30 over hypotenuse, good. Root 3 over 2. Root 3 over 2. Sure thing. Cos of 60, if you could see the one on the top, cos of 60 will be 1 over 2, yeah. Adjacent is 1 this time. Hypotenuse is always 2. Tan, we're using TOA. Tan of 30.
1 over root 3.
Yeah, good. 1 over root 3. Opposite over adjacent. 1 over root 3. 1 over root 3. Tan of 60.
Root 3 over 1.
Good. Yeah, root 3 over 1, yep. So let's start off by writing root 3 over 1. Yeah, which simplifies to root 3, yep. So this is actually one that will simplify because root 3 over 1 can just write much more simpler as root 3. I was going to put like 45 here as well. So I was going to do like sine of 45, cos of 45, tan of 45. So out of interest, what would sine 45 be? Out of interest.
1 over root 2.
Yep, 1 over root 2. Yeah, good. Sine of 45. And what would cos of 45 be?
1 over root 2.
Good, yeah, 1 over root 2. And what would tan of 45 be? Yeah, 1 over 1, which equals 1. So that's, if you want, out of interest, that's what those ones would give you. Okie dokie. What I might do is I might just kind of pause it there. Yeah, I'll leave, this one's a bit of an interesting kind of proof. So I'll leave that one there.
We're all wearing scrunchies.
I'm not. Oh, that's scrunchy. What Isabella's